All right, let's get started. We are rusty with Zoom. I'm rusty with Zoom. Maybe I should put that on all of you. I'm Professor Anna Williams. I'm astronomer here in the physics department, and I'm pleased to see such a wonderful and large group of people to kick off our first seminar of the year. So to kick things off, we have our very own Professor John Cannon, and I realize I should have looked up your history, but I know Iowa University is a very important place for John. Did his undergraduate at Iowa University and your PhD at Minnesota. You were in Germany for some postdoc and Wesleyan, and that's where I met John back when I was an undergrad. He was doing a postdoc with my undergrad advisor. He took me on my first observing one at 15. Fun fact. So, without further ado, I will pass it off to John, who's going to tell us all about the awesome things that we're doing with the Macro Consortium and the Robert L. Mutel telescope. For the folks on Zoom, I've muted you all. For now, make sure you stay muted. Once we have questions, I will take off mute, and we'll be happy to moderate questions between the Zoom room and the people in person. All right.
Okay, good. Thanks, Anna. Thanks to all of you for thanks to all of you for being here. As you can tell from Anna's introduction, astronomy is a small world. And it's very important to acknowledge that people play a critical, if not foremost, role in making astronomy what it is. And today is a story about people. So I've been here at Macalester now. This is the beginning of my 18th year on the faculty. And it's a little embarrassing and scary to say that out loud. But I've been surrounded by great people and great students here, and I feel like we've done some wonderful things at Macalester. And I can honestly say that this endeavor that I'm going to talk to you about today is the one about which I am the most proud. This has been a labor of love. It's been a kettle that's been boiling in the back corner of my career since I started. So going back to Anna's comments about how we met each other when we were much younger, I met the folks that are important in this consortium when I was very much younger, and those relationships have remained throughout this time. Before we start, I want to make sure that you all hear this loudly and clearly. If you have questions, please raise your hand. Unless you're on Zoom, you're cut out. But if you have questions or comments, please interrupt me and ask them along the way. And I want to give special acknowledgement to all of my colleagues at the other institutions. The work that I'm going to tell you about today is certainly not anything done in isolation. And so all the folks here at Macalester, both Anna and Brian, have played critical roles in the success of Macro. My colleagues at Augustana, Co, Iowa, and now Knox have been very, very important in standing this consortium up and bringing it to the level of success that I'm proud to be able to tell you about today. So to kick things off, I thought I would start by embarrassing myself, if I haven't already done that, by showing an image, Eric, by showing an image, okay? My pointer doesn't work, so we'll have to do this, I guess, the old-fashioned way. By showing an image, okay, of myself when I was many younger younger years, and we're following in the footsteps of perhaps the titan in the field. Professor Robert Mutel was another of those individuals that I was very lucky to have crossed paths with early in my undergraduate education. So like all of you, I was an undergraduate. I took some astronomy classes. I said, wow, this is really cool. I want to do more. And I just kind of kept doing. And I was lucky enough to benefit from a little bit of nepotism, I think. I was in the right place at the right time. And Professor Mutel, who really was a visionary, looking forward with this new bourgeoising World Wide Web that no one had really heard of and no one really understood what the power of this was going to be, and said, here in Iowa, it snows all the time. And I can't use my telescope most of the time. But I can build a telescope thousands of miles away in a better site and use this World Wide Web to run it. And that vision was very powerful. And I was lucky enough to be part of the very first iteration of the Iowa Robotic Observatory in 1997. So if you squint your eyes, you'll see a John that has a lot more hair there. And that was the very first telescope still on campus. And then we took it to the Weiner Observatory where it's now housed. And you can see an image of myself and now my colleague, William Peterson, who's also a faculty member in macro, in that picture. So we were very lucky to be part of this first endeavor. And then when I left Iowa and I pursued my own research career and my teaching interests, I watched as Robert continued to develop this system over the intervening 20-some years with a continuous stream of development, both technological and coding-wise, to bring this to a level at which we can say with authority, this really is one of the best robotic telescopes in the world. At least the best robotic telescope that serves the undergraduate community. And so after Robert retired, we sort of knew eventually he would retire, but you know, he took it as far as he's a machine. He kept going and going and going. But eventually he said, you know, I want to go ride my bike instead for more time. And so William, who's in the picture, myself and James Wetzel, now 3 faculty members at Augustana, Co. and Macalester, came together and said, let us see if with 3 we can make 1. And so the 3 of us attempt to emulate what Robert has done so well all these intervening years. So we launched this consortium in mid-2022 and called it MACRO, the Macalester Augustana Co. Remote Observatory. And this observatory is what I'd like to spend most of our time talking about. Now my clicker works again, explain that. So this educational and research consortium takes advantage of the RLMT located in Arizona. So this is just a flyover, watching us look down toward Arizona from our location here in the Midwest. Let's zip over. And now, borrowing a video made by Mark Trublight, who's on the call here, we see the Weiner Observatory. This is a roll-off roof structure housing 7 or 8 concrete pads, most of which were full at one point. The structure rolls back, and Mark can correct me if I get the trivia wrong, but at one point this was the largest rolling roof structure in the state of Arizona, until the Arizona Diamondbacks came along, and it's hard to compete with that. But at 5,000 feet elevation with marquee observing conditions, we have access to this facility remotely, and we can use it to do amazing things. So the second part of the video flies over the observatory looking to the north, and I'm going to pause it right here so we can have a nice vantage point looking at pad number 1. If you think back to the image that you saw of me when I was young, standing in the corner, that was right here. And the University of Iowa Telescope, now the RLMT, has occupied pad site number 1 at Weiner contiguously since it opened. And this site, being the southernmost, has the best exposure to the southern-facing sky. And we have wonderful observing conditions by comparison with what we have here in the Twin Cities. We average somewhere between 200 and 250 clear nights of observing per year. We have observing conditions that are at least a factor of 2 better than what we typically see here in the Twin Cities. And this enables us to do amazing and magical things with our observatory. So let me break this open now, and let's think about what the RLMT is. Henceforth, I'll refer to the Robert L. Mutel telescope as the RLMT, just for short. This is an f6.8 Dahl-Kirkham-corrected plane wave system, and it operates on an MI750 equatorial mount. That's very important. That means that we only need to drive 1 motor, because the angle between the yoke plate and the horizontal is equal to our latitude. So as objects move across the sky, we only have to drive in right ascension as opposed to declination, and allows for simplification of the system. Here's an image of the RLMT, and looking up at the sky here, the photons come from the sky, strike the main part of the mirror, move to a secondary, and then back through a hole in the primary mirror to our collection of instruments. This is our old instrument suite. The new instrument suite comes on the tails of a Herculean upgrade that occurred during the spring semester of 2024, and I'm going to tell you a lot about that. Here now, looking at the back end of the telescope, is our industrial grade focuser. This is brand new from PlaneWave because this Titanic camera weighs so much. And then in between that focuser and the camera are all manner of accoutrement. 2 filter wheels with a rich stock of broadband and narrowband filters, and a very unique set of prism spectroscopy tools. There's also, as you see here, tubes going down to the floor, hooking up to this liquid cooler. And this chiller runs ethylene glycol through the system and operates a -80°C chip, regardless of observing conditions. So here's our own Will St. John playing with the filters. Our contiguous Sloan set goes from U prime all the way out to Y prime. That means we have more or less contiguous coverage in the broadband photometric filters from about 300 nanometers to a micron. We also have a suite of narrowband filters that sit on the 3 to 2 de-excitation of neutral hydrogen, and then photoionized lines of oxygen and silicon. And we also have broadband color filters. What makes the RLMT, one of the things that makes the RLMT really unique, we okay?
Yeah, I just noticed that this is mirrored,
Ah,
so
okay.
it's the, yeah, go ahead.
Okay, one of the many things that makes the RLMT unique is the capability to shift from imaging to spectroscopy on the fly. And this is actually quite novel. If you go to a big observatory and you say, hey, I've been taking images through my filters and now I want to shift over to spectroscopy, oftentimes there's a human who has to go and move some very large piece of equipment, and it takes hours or perhaps days to do this kind of shift. We can do it in one swell swoop. With a click of a button, we can move that filter out of the optics path and move the prism in. And Professor Mutel and now a tenured scientist at NRAO named Dominic Ludovici were the brainchildren behind this. These two tall top hat looking objects are the prisms. And those prisms look like this. On the left is the low resolution prism. Low resolution meaning modest spectral resolution, but broad spectral coverage. And in the spring semester of 2024, we commissioned the new high resolution H alpha prism. This was also the result of significant investment and time on the part of our consortium to design, fabricate, commission, and test this new observing capability. This dispersive element sits here in the center of the 3D printed housing, and this one is actually cemented in between two prisms. I'll talk a little bit more about this and showcase some of the science that we can do with this momentarily. So to summarize then, what is the RLMT? The RLMT is a very powerful telescope located at a marquee observing site with an agile and unique instrumentation suite. And this enables to do astronomy in a completely different way. We can envision a curriculum where we base our projects on real science. Sciences of interest to the community outside of our laboratory exercises, and we can publish those results. Importantly, our students have guaranteed access to this instrument, and so it makes it a real showcase for the curriculum at both the introductory and the advanced levels. So the things that Macro has enabled, I don't think we need to elucidate these in great detail, but of course this is a transformative addition, right? This is something that we could never do with our telescope here in the Twin Cities. Why? Because it's snowing. And we're surrounded by 4 million people, and it turns out people love to make light. They love it. It's their favorite thing in the world. Lights are always on, right? And so there's little that we can do about our urban environment. So let's go to Arizona instead. With that, we get this dramatic improvement in image quality, sensitivity, seeing all these things, which allows us to envision that curriculum, and we have access to this new kind of technology to put our students in the line of fire with these techniques that are at the forefront in big telescopes now. So here's a beautiful image of the Rosette Nebula taken with our telescope. We won't spend a lot of time interpreting this, but I'll sort of wow you as we go along with these types of images. Okay, so why are you all here? What do the students get out of this? Okay, I'm going to show you some images of students enjoying, at least I hope they're enjoying, their time working with macro-related things. These are the students that were enrolled in a topics class. That might sound familiar to some of you. I came to all your classes today and I talked about a topics class, okay, so this could be you a couple of years from now. Notice that it's not just me and a bunch of students, Brian, Jay, and Anna are all in here as well. And these smiling students suggest, hey, I was sleeping last night. Check that out. I can do science while I'm sleeping. And that's a tremendous advantage because if you go upstairs, right, we don't have this robotic observatory upstairs. And to do this kind of science with our telescope upstairs, we have to stay up until all hours of the night, right? And we don't want to do that, we'd rather go to sleep, okay? So here's some students on site last fall. We can still operate it hands-on. Ergo, the pictures of students at the telescope. There's no better way to learn the system than to get the dirt under your fingernails. But when we want to sleep, we just use a remote access computer and do it from afar, okay? And then finally, and what I think is most important to highlight here, is that we can design projects that have legs. These projects go beyond a curriculum that's based in the classroom. So these are the student presenters at the American Astronomical Society meeting this past June 2024 in Madison, Wisconsin. We're standing on the Monona Terrace looking up at the state capitol, and everyone is again smiling, hopefully having a good time, after they've presented research posters which were based on classroom experiences. And I think that's quite a powerful statement to be able to make. Behind the scenes, there's a lot of things that have to happen for macro to operate. So on the left is an image of obscuration in the interstellar medium. For those of you that know me well, you might say, this looks like some dark voodoo, right? This looks like some schmutz. And there's some dark voodoo that has to happen behind the scenes with macro as well. So we're lucky to have one of our consortium members, actually an undergraduate from the University of Iowa, who's now moved on to the PhD program in astrophysics at the CFA at Harvard, wrote PyScope. And PyScope is an open source software package that operates telescopes robotically. And macro made this. We also have access to the expertise, primarily from William Peterson and James Wetzel, to server operation. So we have a cloud server-based solution, which takes images from Arizona. They're uploaded to our server, calibrated, and made available to students within minutes of data acquisition. So all we need to do is come up with a clever idea. What do I want to do with macro? Okay, write my little script, I go to sleep, I wake up in the morning, right? And I'm eating my breakfast burrito or whatever, and I'm looking at my brand new data that's taken a couple hours. Right? And so this is pretty fantastic. So on top is an uncalibrated image, and on the bottom, a calibrated image after Chronos has had its way with things. We named it Chronos, and I thought this was kind of interesting to bring this forward. The name Chronos was chosen because it's, of course, the Greek god of time, but also that character that supplanted the father. And I thought this was kind of interesting because Chronos took over from the former server, and we took over from Iowa, so we sort of ate our father, if you will. And then also, Chronos was the daughter of Gaia, and of course, Gaia is this major survey unveiling the structure of the Milky Way. So there's a lot of trivia built into the name, but it's sort of our workhorse throughout the day. Okay, so I felt very proud of myself here. I wrapped text and I made it different colors, and I'm showcasing the color image that's taken with new background. And I did this conscientiously because this last year has been a whirlwind of activity for the Macro Consortium. Many, many things have happened. So I chose the multiple colors to suggest lots of things were happening. And for the next N minutes, Anna might get mad at me on how many N is, but for the next N minutes, I'm going to attempt to wow you with the accomplishments that Macro has had this past year. Okay? One of which is, of course, our ability to make amazing images. So Alexis Riggs from Knox College made the image that you see here. This is NGC 2903, a near-face on a spiral galaxy. It might look something like what the Milky Way looks like. In the wee hours of the morning, I was thinking about spinning this for added effect, but I decided that might be too much. So first, the upgrade. As we called it, again, in the wee hours of the morning after working for many days in a row, more or less without stop, we called it one upgrade to rule them all. And yes, we're nerds, but we felt very excited about this because the image of NC 5055 in the lower right corner is gorgeous. So what did we do here? We took the former back end off, primarily got rid of our CMOS camera and replaced it with a heavier but higher quality CCD detector. I won't bore you with the details if you want to learn more about that. I'm happy to talk to you about it. But because my colleagues got a kick out of it, I was flexing different kinds of muscles. So Alex and Philip were really the brainchildren here, but others of us were doing things that, to first order, you don't see us doing very often. So here's John drilling a hole in the wall, which evidently was worthy of taking a video of. Here's John cutting a giant piece of sheet metal. And so we were like really getting some things under our fingernails, lots of which were metal shavings when we were planing and printing plates. But this was a highly successful upgrade, and the results are quite dramatic. So on the left is a signal to noise versus magnitude plot. Remember, astronomers are weird, right? Astronomers love to do things upside down and backwards. So when we talk about something that's bright, it's actually a smaller number, and we do it all in logarithmic space, so just to keep you on your toes. But effectively, think of this as brighter, fainter, lower signal to noise, higher signal to noise, in different filters colored by the different colored dots. So we have exquisite signal to noise up to limiting magnitudes of, say, 19. And let me say this number loudly so that we all hear it. 5 magnitudes is a factor of 100 in brightness. And the limiting magnitude that we've ever reached with the telescope upstairs on the roof of this building is 16. And we can do 16 with our eyes closed in Arizona. So it's rare in science that you get to go from one level and quantum leap to another. And that's exactly what macro gave to us. We have very well-defined photometric 0 points. I won't bore you with this, but the numbers are quite important and they're quite robust. and our most sensitive filter at about 22.5 magnitudes in G prime. So the back end upgrade was highly successful. What came next? The design and fabrication of the high resolution prism. So this is William Murillo. Worked with my colleague William Peterson. Everybody's named Will or Bill. It's kind of strange. At Augustana College. Now he's in a graduate program out in California. And William helped us to fabricate and design this prism all the way down to first principles, where we're saying if we put this system to work in certain conditions, what results are we going to get?
What?
There's an isometric drawing here and all the ray tracing and angles and so on and so forth. This was a lot of work. This took us about a year. And we had to commission the fabrication of this element. So went out to a photonics company, they made it for us, brought it back, we had to put it all together, and then of course we had to make it work. So that's what I spent the vast majority of my time in Arizona doing this past spring, and the results that we have are quite dramatic. These are spectra that Anna made. This was in a poster that Anna presented at the AAS meeting. We'll show more results from this momentarily. The H-alpha prism cleanly separates multi-peaked BE emission star lines, gives us exquisite velocity resolution. So take measure of the x-axis here. It's amazing how broad that line is. And for those of you that saw me earlier today, we're talking about how these rapidly rotating massive stars are decreasing mass. This velocity resolution, well measured and much, much larger than the spectral resolution of the system, plus or minus hundreds of kilometers per second. And it's difficult to wrap your mind around exactly what this system must look like. We can also turn that eye on active galaxies. So the image at the left is an image we took with our telescope of NGC 4151. This is a Sept galaxy. That means that there's an accreting supermassive black hole in the center. These have a bad rap. Like, oh my gosh, they're eating all the stuff. They really only do anything if there's stuff there. It happens to be their stuff in this one. And so that stuff is accreted and it turns the center very bright. So when that bright center is pointed at you, you can see it from great distances. So the low resolution prism, again, broad spectral coverage but low spectral resolution, blown up to show that the new H-alpha prism cleanly separates multiple peaks in the H-alpha emission line. And that line at its base is very broad. This can inform upon the kinematics of the gas moving around that central supermassive black hole. Wow, John, this is great. Okay, macro is also a curricular centerpiece. So here's an image that I took. It's a little bit hard to figure out where we are. You might say, this doesn't look like macro. This is at the Arizona Mirror Lab on the University of Arizona campus when our Physics 440 group this past spring went down to the RLMT and we took some tours of nearby facilities. I won't have time to talk about it, but we're standing above one of the 8.4 meter diameter primary segments for the Large Magellan Telescope. This will be the most powerful telescope in the world, and this building is crazy engineering. So for those of you who are like, I don't really think I want to work with data sets my whole life, I want to go build things because I'm a physicist or I'm a rocketry person or whatever, here's your chance. This is science at its largest, right? We're talking about hundreds of millions of dollars of engineering just to make the mirrors. And then you have to build mounts and put it on a ship and take it to Chile and all these different amazing things. Okay, and everybody looks appropriately wow, right? Likewise, my colleague, Professor Natalie Harburg, second from left at Knox College, drove a very rich curriculum in her version of observational astronomy this past spring semester. Lots of projects from this class went to the AAS meeting where we took this picture, including the pretty picture of NGC 2903 made by Alexis here, shown second from right. Then, perhaps the flagship accomplishment, if you will, if I had to say, what did you do this year that was most noteworthy? We went to the AAS meeting, so I'll henceforth refer to the American Astronomical Society as AAS, the 244th meeting of our society. And at the invitation of the AAS vice presidents, the Macro Consortium was selected to give what's called a special session. And this special session is a 1 hour and 90-minute oral presentation to anyone interested about our consortium, and a supporting poster session where individual students can showcase their research results. This is our entire group, lots more people here, including Professor Mutel off here at left. And almost everyone who was present at the meeting was in this photo. Some folks were doing different things at this time and couldn't be present for the photo, but it's kind of like herding cats, you know, when you've got 35 people in your consortium and you're like, can everybody be in this one place at one time? And we missed a few, but okay, you get the point. We were there and we had a lot of fun. The speakers were these. So there's, of course, myself, William Peterson, our own Anna, Here's Will Golay from Harvard, Natalie from Knox, Philip from Iowa, and James from Co. And this is immediately before or after, I can't recall, the oral session, but I don't want to focus on that, I want to focus on the action. Okay, so these are our students. These are our students out there presenting their research results to the astrophysical community in the poster session. And Macro brought forward 20 posters, 20. So I would have to go back many years into my IIAS repertoire to dredge up 20 posters from my own research students. But our consortium comes forward with 20 of these at one meeting. 14 of them were by student first authors. So I'm enormously proud of this. I think this is an accomplishment that I want to do again, maybe under the auspices of Macro, but I wouldn't have thought this was possible without a consortium like this one. So the 14 students who presented these posters are here. I grabbed images where I could find them of all these folks. And I believe the 7 people in the room, I'm going to embarrass all of you now. I'm going to showcase your posters. But there's, let me just say that again, only 7 of these will be brought forward out of the 20. Okay, so this is just a subset. We're talking like 1/3 of what we were doing in Madison. Okay, so all 20 of those posters are here. I'm not sure exactly how this is going to look, but I want to give it a go. When I post the PDF file, these should all be links, and the links will go to the dynamic version of the poster. So this happens to be Lila's poster, and there's 3-dimensional content in here, including a data cube that we compared against for Lila's poster. So I'm only going to be able to show you just a scraping of the highlights. There's so much more here, and there simply won't be time to go through all of that. Hey, it worked. So the eight posters that I'm going to showcase here, did I say 7? I meant 8. I hope all 8 of these folks are in the room today. And even these 8 showcase a dazzling array of science. We're not just doing the same thing over and over again with 20 students. We're doing 20 different things. Okay, so this made for a little bit of mild schizophrenia for me and Anna and everyone involved getting the posters ready. I have to admit that was true. But at the end of the day, we were able to show these posters, almost all of which derive from classroom experiences. Okay, so imagine the next laboratory section that we work on, and then you take the results of that laboratory exercise, instead of writing a report and we turn it in and we get a grade on it, right? Let's go to a national meeting and tell our professional colleagues about it. That's what we were doing here. First up, our own Brian Adams has long had an interest in asteroids. So here are 2 light curves of asteroids. Let me make sure we all understand what that phrase means. Light curve is the change in brightness as a function of time. So plotted on the y-axis is brightness. Remember, astronomers are weird. So smaller numbers are up, and that means brighter, which is weird. So the average is getting fainter, brighter. And this one looks kind of regularish. This one, not so regular. So what's happening here? We have this asteroid, it's tumbling, right? It's rotating about some morphology. And the light from the sun bouncing off the asteroid coming to the telescope, and we see more or less reflective material as the asteroid rotates. So we can model these, and Professor Williams, of course, had a very successful first-year course that, I think with Dave as well, built a model of illuminating an object and attempting to tie this to physics, right? To actually say, here's the object that gave us flavor. Matthew Brodsky, I think, is here in the room. Where's Matthew? There's Matthew. This is a supernova 2024 GY, a type 1 supernova that detonated in NGC 4151. NGC 4216, sorry, I got the number wrong. And a type 1 supernova is, of course, an accreting white dwarf that exceeds the Chandrasekhar mass limits. It can no longer sustain its own gravitational acceleration, and it goes boom. This is a cosmological candle. Multiple Nobel Prizes in physics have been awarded for this science. Why? Because we understand the scale of the universe, and we understand that the universe is accelerating due to the presence of dark energy, and that comes from type 1a supernova. And so we had very successful time examining the decline in the brightness of this object over time, including the characteristic iron emission line bone. Exoplanet transits. Here's where we have a star and a planet that moves between us and the star. The star gets a little bit dimmer. Not very much, but a little bit dimmer. So if you have keen eyes here, you'll see this is on the order of about 0.5% in change in flux. These are baseline stars. This is the planet. It happens to be TRES-3, a planet that's orbiting a star much like our sun, a little bit less massive. but bigger than Jupiter. And we can do these exoplanet transits relatively routinely. I won't say they're easy, but we can do them. This cataclysmic variable, YZ Cancri, is a white dwarf accreting material from a donor star, typically a main sequence red dwarf. And importantly, this is a weak magnetic field object. And so that stream of material forms a disk, careful now, an accretion disk. Contrast that with the decretion disk that I talked about with most of you earlier today and more to come later. That accretion disk funnels mass down onto this disk structure, and the competition in brightness between the donor and the recipient star causes this volatile shaking of the light curve. And Kalev led the effort with this project. For reasons that are still a little bit mysterious, let's imagine the properties of that white dwarf are slightly different. Let's imagine the magnetic field is slightly stronger. This object doesn't form an accretion disk. Why? Because the magnetic field is so strong that the ions moving from the donor star follow the magnetic field lines. And it rains down on the object in tubular stars that kind of looks like it's falling on a pole, ergo polar. They're also strongly polarized systems. So as a function of time, this light curve taken over about 8 hours, derived by Kane, shows this very strong periodicity of the source. This is a geometric effect, and I'll tell you how we know that later on today. Star formation in this galaxy, you all know, those who know me know that I love galaxies, they're the best thing ever. And this low mass galaxy, we took some RLMT data, we used our narrowband filter to tell us where the stars are forming, that's this image on the right, and we compared it with new images of the source taken with a very large array interferometer in New Mexico. So over here, we're seeing the location and contours of the gas, the neutral gas, versus the photoexcited gas where this turns bright. And there's all manner of interesting physics related to the star formation rate, surface density, and the way stars form in these extreme environments here. Will St. John was interested in clusters. So this is the globular cluster MC5897, a collection of some millions of stars. And by smoothing the data and fitting radial profiles to it, we can derive structural parameters, the compactness parameter, the mass distribution in the cluster, and all manner of interesting things. And finally, last but not least, our own Edward worked on eclipsing binary stars. This V1024 Hercules system is two nearly identical stars because the eclipse depths, as one star moves in front of the other, is almost the same one star to the other. So similar, in fact, are these stars that depending on where we fit the baseline, we could say one's the primary, one's the secondary. So it's a very intriguing system to try and learn more about. So I think at the end of this, I've probably showcased to you that the AAS was a pretty amazing experience for us. Okay, we asked for some student feedback. We asked them to anonymize it. So I actually don't know who wrote these. Some students who were there, of the 20-some. Here's my colleague James with Amit and Alexandria, and of course Will and Lila are here hitching a ride somewhere, it looks like. But we think that overall the AAS meeting was an important showcase and also an important turning point for our consortium, because it demonstrated for us something very, very dramatic. That we can not only serve classes as we originally outlined to do in our operating agreement, but we can serve classes and do research. We can change the curriculum and have that curriculum be research-based. And that's a really amazing transformation. I'll go back to the multicolors now because we're still doing lots of things from that whirlwind year. This past summer, we launched our inaugural macro summer program. This is the idea that we have lots of individuals from across our institutions that want to do research with our data. So we thought of and conceived of this interinstitutional research campaign focusing on an object that looks a lot like the image you saw before. In fact, it's the same very object. And so based on the results from Kane's project, where's Kane? Kane's sort of the founder of the feast here. Kane's plot on the left, Kane's plot on the right, showed very strong periodicity in this STLMI object. Located in the constellation of Leo Minor, LMI, it's object ST. It's kind of a boring name. You say astronomers, you have the worst names, very large array, so on and so forth, okay? But here, this periodicity is very, very strong. And we wanted to dig more deeply. What more can we learn? So we asked a simple question. Are these objects variable in other portions of the electromagnetic spectrum? And there's a pedagogical opportunity here, right? Because we can take our RLMT data and we can combine it with telescopes from other parts of the electromagnetic spectrum and expose all the students to radio astrophysics and optical astrophysics in the same project. And so that's what we envisioned doing. We said, okay, let's go to the VLA and ask them for some time to observe this source at 10 gigahertz. That's a wavelength of a few centimeters. So the VLA is down here looking up at our students. The RLMT is down here looking at our students. And importantly, because of the scheduling flexibility of our telescope, we were able to acquire data with the RLMT at the same time the VLA was observing the source. Now, on a competitively scheduled telescope, this would be next to impossible. You have to give a very strong scientific justification for why you want these observations to run with that giant workhorse over there and that giant workhorse over there at the same time. But yeah, it's our telescope. So let's go ahead and do it. And so we did that. And this was a very rich experience. Here's just an image taken of one of our meetings. Of course, we had to meet virtually because we've got students scattered all over the place, right? And here's our image from the VLA. And you might say, John, this is so boring. Look at how boring this image is. It's just a dot, right? And I would argue, there's so much physics in this dot, so let me wow you. The VLA data cover a broad range of frequencies, and were taken over the course of about 2.5 hours. So plotted on the x-axis is time, it's a light curve. Plotted on the y-axis is the spectral bin, that's frequency. And we see as a function of time, the source got brighter at every frequency. There is a broadband modulation of the flux density at 10 gigahertz. And what does this tell us? It tells us that it cannot be anything like a maser mechanism that's giving rise to this. If it were a maser, it would be consolidated in frequency space, but it's not. Okay, so what else can we learn? Going back to the wizardry that is Kane-Rinkowski, Kane made this combined light curve of the RLMT and VLA data on the same axis because the data were taken at the same time. And while we didn't catch the beginning of the observation, we certainly caught the end. And the optical variability, that's the colored lines going up and down here, are out of phase with the VLA data. The peaks are not at the same time. And if the peaks are not at the same time, then the simplest interpretation is a geometric one, where the objects, because we already know they don't eclipse each other, have some sort of hotspot mechanism. The hotspot is that magnetic tube, if you will, that connects one object to the other. And if you have keen eyes, you'll be able to see as the larger donor star goes up, you'll see an area on the front that has different colored pixels. That's the simulation of the hotspot. And likewise, on the other star, there's a few little orange pixels, the simulation of the hotspot of the donor star. And so Theo, where's Theo? Theo was working hard on this model set with us this summer, and we're sort of deep in the sauce with the interpretation on this object right now. So the summer program, like the other things I told you about, was quite a great experience. So I've given you a lot. What's next? Okay, in about 2 weeks' time, we're going to be going down to Arizona to bring the telescope out of its sleepy state. Right now, it's in the monsoon sleeping state because the proclivity of lightning strikes in southern Arizona in the summertime. But the Weiner Observatory is located on Milky Way. And I'm not making that up. It's actually the address. It's where Mark and Pat live. Mark's on the call. And this is an image that Kane took looking up with his phone to the night sky with the Milky Way sign in the foreground. So we're going to go home. And it's always a pleasure to go down to the telescope. We have a wonderful time there. And we're going to do all manner of things, including getting a lot of grease under our fingernails. We're going to bring the telescope back to life in just a couple of weeks. And then once we do that, the next year is going to be chock full of interesting things. One of which is the continued commissioning effort for the integral field spectrometer. So right now we just have these in-filter wheel prisms. The integral field spectrometer is a much more complicated system where we actually have 19 fibers. So those of you who have already taken modern physics or are taking it now, you will remember, or you'll see it soon, excuse me, the fiber optics cable that we use, and you point it at the light, and you get a spectrum of what's in the light, you take it down, and there's no more light, right? You go back and forth and say, wow, I see the spectral features going on, right? So we have 19 of those fibers that see the sky. And then the photons follow those fibers into the IFU, and there's this turret that rotates different dispersive elements into and out of the line of sight, so we can disperse the light on a spatially resolved basis. Which means we can do things like look at the kinematics of gas and nebulae and galaxies on a spatially resolved basis. And having an IFU on a small liberal arts college telescope is next to unheard of. Turns out there's a reason why. It's really hard. It's really, really, really difficult to do this. And so we're deep in the sauce with working on this. But Philip Griffin, in his PhD work at the University of Iowa, has taken ownership of this project and come up with a lot of clever ideas for how we're going to do this. You'll remember from the very first image that I showed you, the back end of the telescope, the 3D printed housing. and the oblong red and gray structure that was hanging off the side, that's the pellicle system. And the pellicle system is just a beam splitter that we put in there after the 45-degree mirror to move light to the fiber bundles and move light to a reverse illuminated fiber optics pattern on the sky. And that allows us to show where the patterns are located on the sky to position our fibers. So Philip is working very hard on this to demonstrate that it does work. This is a spectrum that Philip took a few days ago of Deneb, quite a bright star. But it demonstrates that we get comparable spectral resolution to what the H alpha prism delivered to us, but over a much broader wavelength range. Dozens of features are measured with confidence in this spectrum, and we're just wetting our whistle here. We're just starting to exercise what this telescope will be able to do with an IFU system attached to it. Then, based on the successes from the AAS program, Anna and myself and others in the consortium came to the realization that we can showcase the results of what we do in the classroom in the research setting. And so we're launching 2 new research programs this year. And for those of you that I did see in classes earlier, I only told you about the second one, the VE STARS program. The top program, let's talk about the one in orange first. The Magnetic Cataclysmic Variables project are STLM-like polar objects that and this is really Anna's brainchild, that we are going to monitor as a consortium over a long period of time. And when we see a source go through what we call a state change, either getting brighter or fainter, we are going to trigger a VLA observation. And the VLA observation will then give us the radio information to help us discern what is the origin of this mechanism, what's the physics of the system at hand. So that's going to be a very rich data stream. It's going to keep us quite busy. As if we didn't already have enough to do, we're also going to be talking about the decreasing fast rotator VE stars. So for those of you that I did see earlier, we talked about these objects, right? Imagine a 10 solar mass star rotating so rapidly that it's losing mass at its equatorial region. It's hard to understand what this could mean, right? And an artist's representation of what this might look like is down here at the lower right. So we're going to monitor these objects both photometrically and spectroscopically over the next year and be able to quantify and qualify the types of changes that these sources go through. And this is actually quite novel. The sources are bright, they're easy to observe, but it's very difficult to observe them in the way that we can because of that aforementioned agility to rotate in our prism spectrometer. So I told you about the opportunity to be a star. So this will be the second time many of you have seen this, but if you haven't, we're going to be teaching, and I say we're because I think everyone in the room is going to be involved with this. We're teaching a special topics course in the spring, just 1 credit, not to overload your schedule, but giving you the opportunity to be immersed in this data stream. And we may very well throw some folks into the MCV program too, we'll see. But the title fits better with B star, couldn't MCV a star, so I should be a star. But this topics class, open to any of you, and I'm seeing a lot of faces for the second time today, and I seem to remember a lot of those faces in introductory level classes, and I think that's awesome. I think that's fantastic. Because this is your first step, right? This is your opportunity to get your feet in there and really hit the ground running. So in case you didn't get it already, here's the QR code to learn more about that class. And as we come to our close now, I just want to finish with an image, and I think it's appropriate to embarrass Kane one last time, because we've said his name quite a lot. Here's an image. If you have keen eyes, you'll see Kane looking up at the sky in amazement and wonder. And here's what Kane had to say about the experience of going down to Arizona. So of course, if you want to learn more about macro, come talk to me, come talk to Anna, come talk to Brian. Read our newsletter, go to our website. But before we break, I just want to ask everyone who's had some experience with macro so far, can you all just stand up? Okay. There's a lot of people in the room who have already been part of this. And for those of you, you look around and say, well, I didn't get to stand up. This is kind of a bummer. You can stand up. And you can talk to these folks and you can ask, how was it? What did you do? What did you learn? Was it amazing? And I hope the answer from all of these folks will be a resounding yes. With that, I'll stop and take questions. Thank you for your time.